Zubin, I'm so overwhelmed by data structures and algorithms.
I understand. It's terrifying, but there's a trick to them if you want to know how to do it.
Today, I have a couple of goals. I want you to understand when we say DSA, we tend to sort of lump it all together, but they're actually two different things. The difference between programming and being able to solve DSA type challenges. They're actually very, very different skills. I'll even talk about why DSAs are used in interviews. The number one reason is it's used as a filter. My trick for DSA is that there is a pattern. Different classes of problems tend to have a recipe of their own. Welcome to Easier Said Than Done with me, Zubin Pratap, where I share with you the tens of thousands of dollars worth of self-development that I did on my journey from 37-year-old lawyer to professional software engineer. The goal of this podcast is to show you how to actually do those things that are easier said than done. Hey guys, today I want to talk to you about the dreaded data structures and algorithms and DSA stuff. Okay, so this is often called DSA, which is data structures and algorithms. And I know, or let me put it this way, I don't know any programmer that's not afraid of them, especially initially, okay? So I know I really struggled with them too at the beginning. Now, today I have a couple of goals. I want you to understand, for those who are really new to this, what they are. When we say DSA, we tend to sort of lump it all together, but they're actually two different things. That's one. The second thing, I want you to understand what use cases and context, like why do we even bother with these things? Are they important? Are they not important? When do we use them? Okay. The third thing is I want you to understand that they're very different skills, and I'll explain why, and to know when to optimize for which skills. When I say which skills, I'm talking about the difference between programming and being able to solve DSA type challenges. They're actually very, very different skills, and one doesn't necessarily imply the other at all. So we'll cover that. And I think once you understand that, it'll take some of the fear of it away, because you'll understand it's a different kind of skill that needs to be developed. It's not about programming at that point in time. It's actually about problem solving. But you know what? Let's dive into all that. Let me share my screen as I usually do. The link to this document, of course, will be down in the description in the YouTube video. Here we go. Okay. So let's get some definitions first, right? Because rather than just lumping it all as DSA, let's consider, let's separate it out. Data structures and algorithms. Okay, let's start with data structures. So data structures are just a way of organizing and storing data in a computer application or on a computer system. And the purpose of that is to be able to access it and use the data efficiently. Now, examples of a data structure, don't think of it as anything fancy. Start really small. When you store items in an array or a list, an array or a list is a data structure. It's a way to give structure and form to your data. Similarly, depending on your language, it could be called a dictionary, a hash, a map, a hash map. That's another way of storing data, right? There's a key, there's a name for a piece of data, and then there's the actual data value, right? Then there are graphs and trees, which are slightly more advanced data structures, and they're often compositions of other data structures that produce this kind of a complex. Think of it as a synthetic data structure, but that's probably not the right word for it, right? So there's the composite data structures. You can combine one or two data structures or more to create a complex data structure, right? And so that's what graphs and trees often can be. Now, those are examples of data structures. So we don't need to go too much into the theory. That's not the purpose here. But the purpose of the data structure needs to be understood as well. So each data structure will have different properties and benefits and disbenefits. And so you need to focus on using the right data structure to organize and store your data efficiently. Remember, that's the purpose of data structures. So some data structures are better at organizing, storing, and retrieving certain kinds of information, and other data structures are better for other types of information, right? But there are always trade-offs. And here's the key point about DSA problems, guys. There are multiple ways to solve a given DSA problem, but then there always, there's an optimum solution, or there is an optimized solution, and you have to make the trade-offs and know the importance of trade-offs. Okay, so for example, what if some of the benefits could be, well, we need to take into account the speed of storing, okay, or it could be the speed of accessing. So storing data can take more time. We're okay with that. But accessing data is much more critical. We want to be able to do that really fast. So that's a trade-off. Well, maybe there's a data structure that helps you store data, okay, but really it's optimized for retrieving data. That's a trade-off you want to make. But maybe you're not worried about the speed of retrieving the data. These are just examples, okay? Maybe you're not worried about the speed of retrieving. That's less important than the speed of storing, but it needs to be stored really fast. or it needs to be stored and retrieved really fast and be, when I store something, in almost instantly it must be available to you in the new updated form. Like, these are different kind of problems to solve, right? So the other problem in data storage and data structures can be, well, how efficiently are we using the computer's memory or the storage space, etc.? But largely memory, in memory being the bit that runs when the program is running, storage being the one that stores in like a hard disk. That's different. So how efficiently are you using the limited available memory space, right? Maybe this could be memory and storage is the better way to think about it, right? The limited memory or storage space, how well are you using that? And that's important when a program's running, right? So that's all a question of optimizing available resources. Like, this is a resource, memory and storage space, two different things, but they're resources and they're finite, there are constraints around them, so we need to know how to use them well. Okay, so that's data structures. Let's talk about algorithms. Now, algorithms is a big scary word, but it's really not. All it means is a step-by-step procedure or a set of instructions that'll help you achieve a certain task or solve a certain problem. In the context of coding, it's often to solve a certain problem and to achieve an outcome. It's basically just a recipe. So when you think about it, even a cookbook recipe is an algorithm. It's a series of steps to achieve a certain dish. That's an algorithm, right? Or if you follow a certain sequence of tasks at work to get a certain result, arguably that's an algorithm, right? The moment you write it down and you realize it's a repeatable process that others can follow, that's an algorithm, right? A process manual, an aircraft checklist, all of these things are kinds of algorithms, right? So in the context of computer science problems and software engineering, algorithms are basically how you write the instructions to the computer in a way that solves a problem. But and again, the purpose is to solve problems and perform the task as efficiently as possible, either time-wise or in terms of the use of scarce resources like memory, storage, CPU, network bandwidth, etc. So you have limited resources, scarce resources, or resources that are expensive to use, so you want to optimize the efficient use of them. And you also want the algorithm to run faster than other algorithms because speed matters. So for example, if the algorithm is to search something, if Google chose a very slow searching algorithm, its results wouldn't come as fast as it does, right? Part of the reason it comes that fast is it uses a combination of optimized data structures and great algorithms for finding information through those data structures, right? So examples of algorithms can be, well, sorting, like I have a list, or I have books on my bookshelf and I sort it by alphabet, by the author's name or by the title name. Or, excuse me, I have, a bunch of people on a basketball team and I want to sort them by height. That's numerical sorting, right? And then algorithms could be to sort, and then you could use other algorithms to search, retrieve, or what's known as traversal, which is you take a complex data structure and you have to walk through that, right? You have to find your way through it, explore the path through that data structure to find the data you want. So that's typically used in graphs and trees and those kind of data structures. So now you'll realize that certain data structures will require certain algorithms to use them, especially the more complex ones, right? So let's say I have a list of things and and it's only 5 things in this list. Okay, let's say it's my shopping list. Now I want to find bananas on my shopping list. Okay, so all the things on my list are stored in a list. That's the data structure. And the process of finding the banana in my shopping list is the algorithm I use to find it, right? Now, if it's a sorted list, like everything's done alphabetically, there may be more efficient ways to not have to go through the whole list, right? Don't need to look at each item. So that's what happens, for example, when I have an alphabetized books on my bookshelf, the algorithm is, well, look for the alphabet. If it's done by author, well, look for the, the T or the A or whatever it is. That's faster than looking at all the books. But if my bookshelf is not sorted, right, then you can do a random scan. But if it's not sorted, well, every look is a random look. Or if it's a short bookshelf, you can go from left to right or right to left or whatever it is and look for the book one at a time, right? So that's faster if it's only 4 books on a shelf. It's not worth the time sorting it maybe. But if there are hundreds of books on a shelf, then maybe you need a better system, right? So then you're combining data structures and algorithms. So that's a simple way of thinking about data structures and algorithms, an optimum way to combine data structures and processes or steps to do things with the data that's stored there, okay? So let's talk about whether or not we actually use this in daily life. Now, actually, before that, I want you to really emphasize or really internalize this point. Algorithms and data structures are 2 very different things. They're different concepts, different use cases, and different mental models. Just because we say DSNA or DSA doesn't mean they're all one thing. Don't club them together too much. It's fine to use it as a hand-wavy description of that class of things that you need to do, but remember they're two very different things. Okay, so when you're solving the problems, split it out that way. All right, so how do we use DSA in daily life? Well, in general, in my experience, it's not as often as you'd expect, and I think this is anecdotally confirmed by most people. It's not as often as you'd expect, given all the hype around it. You don't use it as much as you think, but a lot of it depends on the job or the job to be done. So either the actual work you're doing as part of your role, or on the job or the task to be achieved in that job, right? So sometimes you'll need to learn algorithms to achieve a certain task, but 99% of the time, maybe your job doesn't require it. Okay. Now, my opinion is, and my limited experience in having been at Google and stuff, is that most jobs don't actually require this day to day. Every now and then you'll need to use it, or sometimes you may need to understand it in order to read somebody else's code. And there's another episode that I've done on this podcast talking about how important it is to read other people's code, and the reality that we really read a lot more code than we write. So sometimes understanding these principles will help you in reasoning about other code or in the project you're working on and so on, right? And the other observation is that in general, the bigger and more sophisticated the product or service you're working on, and by bigger, I mean the scale, like how many people are using it. For example, if you have a product that's an API and you're getting only 20 requests an hour, you don't need to optimize too much. But if you're getting 200 requests in a minute, then you probably have scaling problems for your API to be able to handle those requests, your server to handle those requests. So generally, the bigger or the more sophisticated a product or service is, or the more complex the problem it solves is, then involving lots of data, then more likely you're going to be using algorithms and data structures much more, right? And if your company is the sort that has that kind of product, then more likely that the people who are doing it will be using it much more, which is why sometimes very sophisticated, very complex products can have a small team of engineers if they're all senior, because they're all able to handle it, right? And so they may recruit accordingly. So just, different contexts. By and large, I haven't seen it that much. And, I'll even talk about, whether there are lots of interviews use it or not. I think we'll talk about that later on. But let's get back to the question of, so use in daily life. Now, most coders will be writing code that depends or imports other libraries and packages, and often algorithms and data structures and optimizations and helper methods and stuff can be available on these libraries and packages. Other people have written them, maintained them, tested them. They're often open source, and open source software relies on other open source software. And so you can sort of count on the fact that well-used software will probably have these algorithms and data structures well optimized, well tested, and battle tested and battle hardened. And so you can just access those libraries rather than having to write one of your own by hand. Now, it can be really, really foundational for products and services. What do I mean by that? Like sometimes when you're starting out a completely new project and it's all greenfield, right? Then choosing the right data structures and algorithms could set up the company for long-term success, less maintenance problem, less rewriting. So often when I say foundational, I mean it's part of designing a system. At that point of time, you could give a lot of thought to data structures and algorithms. And then once it's implemented and in place, then you're just building the rest of the product around it, right? So often very early teams will need to be good at data structures and algorithms, or at least have somebody on the team that's pretty good at that. Now, once they're built, they form part of the core of the product. And then after that, it needs more maintenance and use in other parts of the code rather than actually writing the algorithm and data structure, right? Sometimes when you're inventing a problem, like when in one of the startups that I worked on before I learned to code, the one that I founded, it was a problem around parking, finding street parking on public streets in the city of Melbourne, and we had to come up with some of our own algorithms and data structures for efficiently working with that kind of data to solve that problem. So sometimes you'll need to come up with your own and understand the trade-offs and things like that. Okay, so those are sort of the day-to-day use cases of DSA, and it's not as day-to-day as you'd expect given all the hype around it. So let's talk about why DSAs are used in interviews. Okay, why is it that, and this is why most people are afraid of them, is because there's a lot of pressure associated with data structures and algorithms. If you're doing it outside of an interview environment, you'd probably find it interesting, challenging, but not scary, maybe frustrating, but not scary. The reason it's scary is because it's used in interviews. And in that moment, for you, it can feel, for all of us, it can feel do or die, right? There's so much importance we place on the interview and getting the job. It has a big impact. So I totally understand why it's scary. But let's understand why it's used in interviews, even if most jobs don't actually use it. Or the interview expectation will be a really high standard of data structures and algorithms solving ability, but you don't actually need that level in your job. So why is that? Well, the number one reason is it's used as a filter. So at Google, for example, they talk about things like role-related knowledge, which is one of the criteria. It's all public information, about, well, do you have enough knowledge to do the role effectively? Another one is general cognitive ability, which includes your ability to think through problems and solve them, right? So they're using these signals in the interview process to assess, well, generally, can this person solve complex problems or not? And one way to do that is through using data structures and algorithms as the test interview questions. So of course, it's not a perfect system. Of course, it's kind of messed up from the candidate's point of view. And of course, luck matters on the day. And of course, all these other factors, and it's frustrating and scary and annoying, and it's easy to hate on DSAs. But ultimately, they're doing it because they have so many applicants. And for every role these days, you'll have hundreds of applicants for the average software role, and only one person is going to get the job offer, right? So to go from hundreds of applicants to one selected job offer means you have to filter everybody else out. And so DSAs are used as a form of filtering. Either you can understand and solve the problem, and it's a learnable skill. So don't get frustrated if you can't right now. In a few months, you probably will. So they just use that to filter out people, filter out candidates, just like any other interview process in the world or any other audition, right? If you're a theater personality or you want to be a singer and you go on audition, they're using certain things to filter out most of the people so they can choose the winners, so to speak, right? But just because someone lost in that process doesn't mean they're bad. It just meant that on that day they didn't do as well as they could have. And they can absolutely do that another time, right? So that's why DSAs are used in interviews. It's filtering. And is it a good system? The jury's out on it. We don't know of a better one. And so, it's what we got. So regardless of whether it's good or bad, the fact is until we find a better one, we just have to work to reality as it is, not how we wish it was. Now, the reason why it's scary is, like I said, it's not just an interview setting. It's also because the actual approach to data structures and algorithms is a complex and alien way of thinking for the average human being, because most of us don't think like this, right? We don't think in these highly abstract concepts. And therefore, it requires practice for the brain to get used to it, to lay down new neural pathways so that you can understand this form of conceptual thinking and abstract thinking. And thinking abstractly, human beings are very, very good at it. But we don't often do it at these kind of levels, and it's a learnable skill. Okay, to think abstractly, to reason abstractly are all learnable skills. We naturally do it as we move from child to adult. Some of us may lose that ability when we get a bit mentally rigid, but 100% we have the basic ability, and it'll come back if you've lost it. And the ability to visualize things I find very helpful, right? So often to understand things in the abstract, we need to visualize it, either write it down or draw diagrams or something, because the visual cortex in the human brain is way bigger than any other part of the brain. And so we are very visual creatures. So visualizing is really helpful to reduce that scariness, okay? Now, algorithms in particular, less so data structures in my opinion, but algorithms are very hard to understand just by reading the code. Because again, if you watch the other episode or you listen to the other episode where I talked about reading code is much harder than writing code, but it's at least as important, if not more important, we realize that reading code is very hard because we'll miss a lot of the context, right? We just see the end result steps. Do this, then do this, then do that, and then do that. Well, why? And what happens, if we're doing it this way, or why is this funny syntax here? Usually there are good reasons, right? But it's very hard to get it just from reading code. So it's really important when you're doing algorithms to first understand the concept and the mental model. And I'll talk about a trick I use later on. But really what we want to do is understand the mental model. And because code has a lot of its rules and the reasoning is hidden, we just see the outcome. It's really important for us to not just read the code to try and understand an algorithm, right? First, we need to understand the algorithm. Then we need to read the code or a few examples of code that implement that algorithm. But first, we need to understand the algorithm very, very carefully, okay? And it's very hard to understand why a step is even needed just by reading the code. So you only have to, understand why a step is needed by understanding the concepts of the algorithm, the broad steps, and then the implementation detail comes later. Now, my trick for DSA is that there is a pattern, different categories of problems. So for example, some problems require sorting. Some problems require holding two pieces of data in computer memory and then comparing them constantly. This is known as the 2-pointer or 3-pointer memory, sort of methods and so on. Some problems require you to maintain a data structure of information. So Dijkstra's algorithm, for example, you need to maintain, past points that you visited. And often, what really helps is understand the class of problem, right? The category of the problem. So for example, if you had to figure out, how to move from houses to houses in a neighborhood in a certain order, well, you could argue that's a kind of graph traversal or tree traversal problem, right? So you have to represent real world problems back into the world of data structures and algorithms. And that's a skill. And you do that by classifying. And how do you classify? To be honest, you just got to do, I would say 10 to 15 of each type of problem, and you'll notice it's a pattern. Right? But you have to stick through the first 10 or 15 before you start to notice the pattern. Once you notice the pattern, then try and apply it to daily life, right? Try and say, well, okay, I'm organizing my bookshelf. That could be a list or an array problem, right? Or I'm trying to find something completely random in a drawer. Well, maybe that's an indexing problem, right? Or, you need to use a hash map to store an index of something. And be aware of the trade-offs, because there's no perfect solution. There are just optimized solutions, right? So the big trick here is to classify different types of problems. Different classes of problems tend to have a recipe of their own, a combination of data structures and algorithms that work well for that class of problem. And you'll find that a lot of real world problems around you are networks of roads, for example, or networks of telecommunications. They're kind of the same thing, because you have nodes and you have connections between the nodes, right? Roads between cities, and connections between computers are kind of the same principles. Cities are like computers, and the connections are the connections, right? So those become graph sort of problems. And so you start to visualize things in that way. It takes a bit of practice, takes a little exposure and repetition to get that. Now, why do I say that programming and DSA are totally different skills? Initially, I didn't realize this. So for my first job, for example, or the first 4 job offers I got, which is right after I finally learned to program, I got all 4 of the jobs I applied for, because I was very intentional, and I teach my students how to do this. But the basic idea is, for my first few roles, it ended up being that none of them required DSA. In fact, when I first became a programmer for the first year or so, I stayed away from places that needed too much DSA. There are some roles that don't require too much advanced DSA, especially front-end type roles or web developer roles. So I did that because I knew that was a totally different skill. And I figured that out through the help of my coach and a few other people. So I would say that the different skills for this reason. Most programmers are not, statistically speaking, are pretty weak at DSA, because it's a completely different type of skill. When I understood that, I realized that just because I'd become a programmer doesn't mean I was good enough to get into FANG yet. For the interview process, not as a programmer, most people are good enough at things with practice, so that's not the issue, but it's a different process. So while I was working full-time as a programmer, I also trained myself on DSA for about 8 months, right? A completely different program of work. That's when I realized just truly how different the two skills are. So lots of programmers can be weak at DSA, and lots of people are really good at what's known as competitive programming, or these hacker rank smashers. And I realized this when I was on the interviewing side. So at Google, for example, I did interview a lot of candidates where they were super good at DSA stuff. They'd cracked the problem because they'd done so many lead code questions or whatever it is. They really understood the problem well, but they couldn't actually program or explain stuff in certain way, or they couldn't solve real life problems in certain way. So they were great at the DSA stuff, weak at the programming. And then people who are really good programmers who couldn't crack the DSA stuff, right? Completely different skills. They built amazing applications. They worked in companies that have built amazing things, but they couldn't crack the DSA on the day. And so that just further gave me proof of the fact that these are totally different skills. Generally, what I would say is, when you're product engineering or building tools, chances are that the day-to-day building skills, the coding skills, the programming skills are more important than the DSA skills, okay? But the reality is, to get the job, the DSA skill can be a little bit more important than the programming skill, because that's what the tests are based on. And this goes back to every schooling system we know, or every testing system we know. It tests a certain subset of skills, and in 45 minutes or 1 hour, there's only so much you can test for. So it becomes heavily optimized for DSA and less for general programming skills. But in general, you need a balance of both to be successful in the job. And good interviewing processes will make sure that you have good, solid programming skills, or at least the fundamentals, and that you can do the DSA on top of it. So for example, when I went to Google, I knew only JavaScript and TypeScript at that point in time, right? And my role didn't require that at all. I didn't touch JavaScript or TypeScript or React or any of that for the entire time I was at Google. It was all Golang, some SQL, a bunch of stuff in Kubernetes, like completely different stuff. stuff. But they didn't care that I didn't know any of that stuff because my fundamentals, in their opinion, were strong enough. And I solved DSA in a way that convinced them that I knew how to solve complex problems using programming, right? So not all jobs require you to have the knowledge of the skill. They may require you to have the programming fundamentals down, but cracking interviews is very much a DSA problem, not a programming problem, right? So separating the two, that's why I think they're two totally different skills. Separating the two is really important in your head. And remember, not all jobs need DSA. So understand the kind of job you're going for and the importance of DSA in it. Like even when I was leaving Google, I interviewed for a couple of really good companies where they were more interested in my knowledge of the tools because that's what they prioritized than my ability to solve some random, completely theoretical problem, which I wouldn't see day to day. It's less about the actual abstract data structures and more about practical problem solving for their business logic. So these are the different types of interviews, the two different skills. I know it's scary, but at the end of the day, by separating out the two skills and not mixing up the two, you can divide your journey, which is what I do with my students, is first be a good generalist programmer. Then you optimize for the interviews with DSA, right? It's a completely different process, completely different curriculum, completely different ways of working, right? And that's why they get the kind of success they do, is because we don't mix these two concepts up. They're very different skills. All right, well, hope that helped, guys. This document will be, as always, in the description. Yeah, keep hacking, good luck.
Do it. Just subscribe. You know you got to do it.